Alright, so let's start building our heat exchanger. First thing I'm going to do is start a new file. For this example, I'm going to pick as my Section 8 Division 1, but of course the process is pretty much identical if we choose, for example, EN 13445. I'm also going to pick ANSI and metric nozzle sizes. And because this is a heat exchanger, the first thing we need to do is we need to tell PVE that we're designing a heat exchanger. We do this on the Design Constraints panel, and we do this using this checkbox here, the Is this a heat exchanger box. What this does, it sets the load cases to be appropriate for the different process scenarios on the shell side and the tube side elements, and it also disables the design pressure and temperature area up at the top of the screen here. That's because we specify those individually on each component, whether it be shell side or tube side. So now that we've done that, we can start modeling, and the first element we're going to add will be the inlet channel head, which will be the left hand end. So I'm going to add an elliptical head. First of all, this is in the vertical orientation. We want to be in horizontal, so let's flip the element orientation to flip to a horizontal. Now we do have some red text in the bottom, but let's not worry about that for the moment because we need to enter in the actual geometry. This is almost 2.5 meters diameter. We need to be a much smaller diameter than that. But before I enter in the geometry, the very first thing I'm going to do, and this is really good practice to get into, especially on a heat exchanger, it's very useful to give each element a meaningful name. Not something that we've used in the previous videos, but in this one I definitely am going to do that because it's very useful on a heat exchanger. Because later on we need to tell PVE which are the shell side elements and which are the tube side elements. With everything having a name, of course, that is much easier. So this will be the inlet channel head. And then this will be, I'm going to go on an outside diameter basis, so I'll change that to OD, and my OD will be 610 millimeters. Okay, so my thickness is actually sufficient, however I am going to adjust this to a 10 millimeter thickness because this will be useful and help me later on. I'm also going to reduce the corrosion allowance to 1 millimeter, and then I'm sticking with SA516 grade 70, but I'm going to change the pressure. I'm going to have an internal pressure of 0.7 megapascals at 180 degrees and an external pressure of 0.05 megapascals at 80 degrees. Okay, no issues shown down in the bottom right hand corner, so let's add the next element, the inlet channel shell. So again, the first thing I'm doing here is giving this a name, the inlet channel shell. And of course, most of the properties have been inherited from the previous component, so the only thing I'm going to change here is the length. It doesn't need to be over 3 meters, it's just 500 mil in length. Next, we'll add the flange, which will be what the tube sheet itself is connected to. So I'm going to add a body flange. And once again, the very first thing I do, add a name for the component. Inlet channel body flange. And then for entering in the geometry for the flange, I'm actually going to go to the perform flange calculation field. Although before I do that, let's change the material because this is 516 grade 70. Plate material not suitable for a flange, so I'm going to clear the material name out. And as soon as I do that, PVE will present the material database to me to select an appropriate material. And I'm going to just go down to the search area here and I'm going to search for SA105. Forging material suitable for our flange. I select the material. PVE then gives me a preview of the material information, including the temperature stress curve. Shown here, looks good to me, so I'm going to say select. We then get the appropriate information, including the allowable stresses for the current temperatures that we specified. So I click OK. Now I can go to the perform flange calculation field, and if I check the box, I get the flange input dialog box where I can specify the flange type and geometry. This is going to be a standard flange, so I'm going to go to this area here. Instead of typing in the information, I'm going to go down here and check the box and look up standard flange data. So I'm going to look up a ANSI class 300. As you can see, there's also a DIN flanges available, but I'll pick ANSI class 300, nominal size 24, and hit obtain dimensions, and the dimensional data is pulled. The only thing I need to pick here is a gasket, fill in the gasket factor and the yield. So I'm just going to hit the lookup button, and I'm going to pick one of the gaskets. Let's say this one here, the third one in the list, the elastomer type gasket, and I will select. So of course, this being a standard flange, no calculation is performed. If you do still wish to perform the calculation, you can uncheck that box. Of course, we've still got the standard flange geometry, but the calculation is run. But down here, as you can see, everything is blue, so there are no issues. The little calculator button can be used if you wish to see the detailed calculation. Okay, so next let's add the main shell. And once again, let's give it a name, main shell. And let's also pick an appropriate material. We're back at SA105. I want to be back at 516 grade 70. So let's clear SA105 from the material and look up SA51670 from the material database and select that. Okay. Okay, let's also just see we have the incorrect outside diameter. It's been inherited from the flange, so let's reset that back to 610. And for the length, I want to go to 2.87 meters. And this main shell, this is now tube side, so I'm going to change the operating conditions. So the internal pressure, it'll be 1 megapascal at 120 degrees, and external pressure will be 0.09 megapascals at 30 degrees. Okay, and there's my main shell. Next, let's put the outlet channel body flange here. So let's add a new body flange, and I will call this the outlet channel. Also, let's reset the material back to SA105. And this flange will be identical to our first flange, so I'm going to go back into the perform flange calculation window, and instead of looking up the data, I'm just going to go and say make this one just like the inlet channel body flange, and hit copy now to copy all the parameters. So you can check all the boxes. I'm just going to leave the default boxes checked, and then hit copy to copy all of those properties from our first flange, the inlet channel flange, to the outlet channel flange, so they're identical, and hit OK. The final thing to do, of course, on here is this is back to shell side. So let's reset the conditions back to 0.7 megapascals at 180 degrees internal and 0.05 megapascals external pressure at 80 degrees. Finally, one more component for the outlet channel shell. Change the material back to SA516 grade 70. Okay, and adjust the length to just 500 millimeters and the outside diameter back to 610. And finally, the outlet channel head, by adding the elliptical head, give it a name, and there should be nothing else to change on the outlet channel head. So there's the main body of the heat exchanger. Next time we're going to add the tube sheet itself. Alright, so we have our main body of our heat exchanger. Let's now add the tube sheet and tube bundle. This is done from the details panel here, so as before in the previous examples that we ran, first thing we need to do is select where we want to attach the, in this case, tube sheet and tube bundle. So it will be attached to the inlet channel body flange, so I will select that and then I will hit the tube sheet button from the details panel on the ribbon. This displays the tube sheet input window. Of course, tube sheets is quite a lot of information required, but the input is separated into various different tabs which we'll go through in turn. Starting with the first one, so let's pick the general information. So this will be an ASME tube sheet, and this will be a fixed type heat exchanger with no expansion joint, and for the tube sheet and shell junction stress reduction option we'll leave as is, or we'll set to none. So, if you remember in the previous video, what I said was you have to tell PV which are the shell side elements and which are the tube side elements. This is done in this listing area here, and you need to check the box for the shell side elements. This is really where giving everything a name becomes very, very useful. See, we have all the element names. If we didn't have the element names, we just have element 1, element 2 with the node numbers. So giving things a name is very useful. Now we only have one shell side element, which is the main shell. So we just need to check that checkbox and only that checkbox. Right. So there's some various other information, service type, radiography type, if we want to user define, MAWP and so on. We can do that here, but for this example, I'll leave those as is, and I'm going to go to the next page, the tube sheet properties. So I'll give this tube sheet a name. I'll just call this tube sheet 1. And the location of the tube sheet is automatically calculated and by default is placed at the far end of the selected element. So that is 171 millimeters, which is the 168 mil overall length of the flange plus the gasket distance. So that's okay, I don't need to change that, but of course you can change that if necessary. So what type of tube sheet do we have? Well, our tube sheet will be this one here, type B, a fixed tube sheet, integral to the shell, but extended as into the flange. When we select one of the types, which is tube sheet extended as flange, the checkbox required for that is automatically checked. But we do need to specify the thickness of the extended portion, so that will be, in our case, 65 millimeters. And then the tube sheet itself will be 70 mil thick. So as soon as we change the thickness of the tube sheet, we get a warning message. Make sure you change the expanded depth of the tube on the tube data tab. That's okay, we've not gone to the tube data tab yet, so I can just click OK on that. Okay, for the rest of the input I'm going to leave a 0, so for the corrosion allowance, the depth of the welds and so on, I'm going to leave those as 0 for this particular example. There's no shell band in this example, and for the moment at least there are no axial loads for the tube bundle pull-out force. If we need to remove the tube bundle for maintenance and so on, you can assign the force that will be applied here in this field down here. But for this example I'm going to leave that out. Which takes me then to the next page, the tube sheet, the tube data page. So I need to specify the number of tubes and the tube layout, which I can do here. I can specify the number of holes and so forth in the tube sheet, or alternatively PV can assist me with this using the tube layout assistant, which is what I'm going to use here. So I'm going to hit tube layout assistant, and accessing the tube layout assistant does require me to save the file, so I'm just going to give this a name. I'll just call it heat exchanger 1 and save it into a suitable location. Upon doing that, the tube layout assistant will appear, and I can specify some information here. So I just need to specify the basic information for the tubes, the tube boundary, the outer tube limit and so forth. So the outer tube limit will be 565 mil. That is based upon a 610 mil OD and a 10 mil thickness, so a 590 mil ID. So let's go 565 for the outer tube limit. Let's have 20 mil diameter tubes with a 30 mil pitch. And just those three values is enough for PV Elite to start laying out the tubes. With the triangular layout, this gives us 301 tubes. Of course, you can try other types of layouts, a square layout for example, but that only gives me 261 tubes. If you have nozzles, you need to provide clearance for the nozzles. You can add distances here, so maybe I need to add in, let's say, 50 mil clearance for a nozzle on top. Again, that would reduce the space available and thus reduce the number of tubes, and so on and so forth. But I'm going to set that nozzle clearance back to 0, and I'm going to stick with my 301 tubes with the triangular pattern. If you have multiple passes, you can also add partitions up in the top section here, but again, for this example, I'm going to have 0 partitions, just a single pass, and I'm going to leave as so. So that's all I need to do. So I'm just going to save the results here of this tube layout, and I'll close the tube layout assistant. And then back in PV Elite, in the tube sheet input, I can just hit the import layout results, and that will fill in the majority of the information required on here. Which just leaves me to specify a few more pieces of information. So a 3 mil wall thickness, let's have a 1 mil corrosion allowance. The expanded portion of the tube, 40 millimeters. And the straight tube length, well, I'm going to measure that between the inner faces rather than the outer faces. And the distance between the inner faces, the straight tube length, is the same as the length of our main shell, which was 2.87 meters. Then that's it for the basic tube data. Let's specify the weld data for the tube to tube sheet weld. Let's have a 3 mil size weld, and let's have a full strength weld, and let's change the allowable joint load method to ASME UW20, which is more appropriate for welded joints. And because this is a fixed tube sheet, we need to specify the maximum distance from the tube sheet to the first support, and then the maximum distance between two supports. So I'm going to say that is 700 mil here and 500 mil between two supports. That's everything for this page. Next we have the expansion joint page, but we don't have a joint, so I can go next to the load cases page. Most of this is imported and pulled in from the basic data that we've already entered, but there may be some information that we need to specify here. So for the max operating pressure, I'm going to put that as 0.7. Temperatures are mostly okay. I'm just going to adjust the mean metal temperature along the length to 90 degrees for the shell and 140 degrees for the tubes. And then I'm going to change the material for the tubes. So default material SA214. I'm going to change this to a material SB165, which has a copper content, so it's better for heat transfer properties. So I need to choose this instance, of course, because it's the sub 5-inch OD. So select the correct instance. There's a SB165, and then that's for our first load case. You can have up to 8 different load cases. For this example again, let's just have one load case. And then finally I'm going to click up here for the reports options for this load case. And for each of the load cases, up to 8 load cases that you process, PV Elite will run these 8 different load cases, and it will run each of them in the corroded and the uncorroded condition. So we have 16 different load cases evaluated different combinations of design and operating temperatures and pressures and shell side and tube side pressures. By default, PVE will only provide the detailed results for this one here, D3, which is the shell side maximum pressure, tube side maximum pressure for the uncorroded case. Typically that's the worst scenario. You can view the detailed results for any of the other cases by checking the box. Of course, PVE will run and give you a summary of all of these, and it's advised not to check all of them, otherwise you'll get 16 very, very detailed load case reports for each of your 8 load cases which you run. So your report will be enormous. So I'm just going to leave the one checked, the uncorroded case. And for the tube sheet input, that's everything. I'm just now going to click OK, and there we see the tube sheets have been inserted, connected to the body flanges, and if I switch to a transparent view, I can also see the tubes in the tube bundle. You could also, instead of going transparent, you can also add a cutting plane with this button here, so we can see inside the main shell. To see the tube bundle, like so. Alright, let's start by adding the nozzles. So I'm going to attach first nozzle onto the inlet channel shell. Select the shell and hit the nozzle button on the ribbon to add the nozzle. I'll give this nozzle a name. Let's call this one Liquor In. And a Shed 40, nominal size 200 nozzle is what I want, and Shed 40 is okay. As we can see, the area replacement calculation passes down at the bottom of the window. So I'm just going to position the nozzle. Let's move it 250 mm along the shell at a 90-degree layout angle. And I'm going to change the flange to a class 300 flange. Okay, so there's my Liquor In nozzle. Next, onto the main shell, I'm going to add 2 nozzles, a cooling in and a cooling out. So on the main shell, attach a nozzle, and let's add the first one, cooling out. This will be nominal size 250. Again, at Shed 40, the area replacement calculation passes. Let's move this 500 mm along the shell at a 180-degree layout angle, and we'll attach a class 300 flange. I want to add a second nozzle onto the main shell, so I go to the Add a New Nozzle button down at the bottom of the window. We add the second nozzle, and this will be the cooling in, which will then make just like the cooling out nozzle. So Shed 40, nominal size 250, all the materials again are okay, class 300 flange. However, we'll relocate this 2.45 meters along the shell and reset the layout angle to 0 degrees. Again, no issues with the area replacement calculation. And if we switch to perhaps an isometric view, we can see all of the nozzles. So I'm going to attach one final nozzle onto here for the Liquor Out, onto the outlet channel shell, and I'm going to make this one just like the Liquor In nozzle. Let's change the name to Liquor Out, and then change the position 250 mm along the shell at 270 degrees. Clicking on the nominal size field will kick in the area replacement calculation, which again also passes. So no issues with the nozzles here. If I jump to orbit mode, I can spin the model around, I can see all 4 nozzles, which look okay to me. Okay, next let's add the saddles, the 2 support saddles, which we will attach onto the main shell. So let's select the main shell. We don't have to switch to select mode, but for clarity I will just jump into select mode, select the main shell, and let's attach a support saddle. So the first saddle I'll call left saddle, but I'll reposition this slightly further along the shell to 200mm. The centerline dimension, see the distance B indicated by the sketch, I'm going to increase that to 900mm. The wear plate is okay as is, and all the rest of the data is okay. If we wish to perform a check on this saddle, we can do that by checking the perform saddle checkbox. And for this example I'm going to stick with the default material and all the default properties here. Of course you could change these if you wish. I'm also going to perform anchor bolt calculations by checking the box here. And 8 bolts is okay, the bolt material is okay. The only thing I'm going to do here next is to pick the bolt diameter. I will click the button here to pick from the list, and I'll pick 1-inch diameter bolts. So that's my first saddle. I'm going to add a new saddle with the button down the bottom of the screen, so I've now got 2 saddles. This is saddle 2 of 2. I'll change the name to right saddle, and I'll make this one the same as the first saddle. So if I hit same as first, that pulls through all the properties to match the first saddle. So here we have the bolt diameter, centerline dimension B has changed, and the saddle has also been positioned appropriately the same distance from the far end of the shell, 200mm, as the same distance as the first saddle. Okay, so there's the input complete. Here in the next final stage will be to run the analysis, which will be done in the next video. And finally, when we click OK, here we can see our saddles. Again, in orbit mode I can take a look, see the saddles. Now the heat exchanger input is complete, ready for analysis, which as I say will be done in the next video. Alright, so let's run the analysis now that a heat exchanger is complete. Go to the ribbon, hit the running man to run the analysis. And the calculations run, and the analysis is now complete. And once the analysis is complete, we now see the output processor. So we have a few reports listed in orange. The warnings and error report is just orange to tell us that PVLite is doing all the calculations internally in imperial units to remain compliant with the ASME code. So that's fine, that's just a warning for our information. We also see warnings on the flanges as well. Both flanges are shown in orange. But the warning here is, as you can see, this warning should not be considered for standard flanges, which ours is, and we see the same warning on both of the flanges. So we don't need to worry about this warning, we don't need to consider it because we're using standard flanges as permitted by ASME 8 in table U3. We see the same warning, by the way. The external pressure calculation report is also shown orange, and that's for the exact same reason, warnings related to the flanges. So again, we don't need to consider that because we're using standard flanges. However, what is a problem is the tube sheet calculation, which is in red. This is the ASME tube sheet calculation. And if we scroll down, as we see the various different calculations for the selected load case. However, all of those 16 load cases that I mentioned are actually run. The design and operating in the corroded and uncorroded case, and we see the summary table for all of those load cases at the bottom. The detailed just above is just for the selected load case, which we had this one here, the uncorroded, max pressure shell side and max pressure tube side. So that's the one we see all of the detail for, and then we see the summary, and down here we see the tube, shell and channel stress summary. And on here we see some issues here in the uncorroded operating and the corroded operating cases. They all fail. So if we look a little bit in more detail at the max ratio column, well, this one is okay. The max ratio is 0.32, 32.5%. This is an issue, 123%, but this one and this one are not issues. So this is the tube stress in tension, so that's okay. This is tube stress in compression, that's where we have an issue. The tube loading, that's okay, and the shell stress is also okay. So our only problem is the tubes in compression. And as you can see, the worst of those is this one here in the corroded case, operating 2 in the corroded case, but all of the operating cases fail. This of course being due to the thermal expansion differential between the tubes and the shell. They're expanding at different rates, of course they're different materials and of course different temperatures. So we have an issue with compression, we have buckling problems essentially with our tubes. So to counteract that differential thermal expansion, we're going to make a slight alteration on the tube sheet, which will be to add, I'm going to close the output, go back to the input, we're going to add an expansion joint onto the tube sheet to absorb that thermal expansion. So all that needs to be done here is if we double click on the tube sheet, and then we can change in the tube sheet input, change to either a thin or a thick type bellows. I'm going to pick a thick type here. Once I've made that change here to add an expansion joint on the expansion joint data page, this is now enabled and I can fill in the information. So I'm going to put this round about in the middle, 1.4 meters along the shell. You can choose to either analyze or specify an existing tube sheet. For this example I'm going to pick existing. Requires a little bit less in terms of the input, and I'm just going to specify the joint OD and ID, which will be 750mm and 762mm, with a 6mm wall thickness, a 1mm corrosion allowance, and with the knuckle, as you can see there's a sketch here to help with the input. The knuckle offset on the inside and the outside, FA and FB, here and here, will be 25mm for both of them. And the knuckle radius itself will be 40mm, again on both sides, A and B. The shell, the cylinder is 2.8 meters, and let's rate this for 8,000 cycles. And for this I'm going to manually specify a spring rate here in the user field, so I'm just going to specify 2000 Newton per millimeter for the spring rate. Okay, and that's all the input that I need here for this particular expansion joint on this heat exchanger. So when I click OK, here I see, here's my thick expansion joint, and all that's left to do is rerun the analysis. So again, hit the running man. Again, the calculations will run. You see the process and the status. The analysis is now complete. And we're once again presented with the output window. We again see the warnings and errors in the orange reports. They're exactly the same as we saw before, but the tube sheet calculation is now no longer shown in red. And if I scroll down past all the detail, just going straight to the summary here in this video example, here I can see the results for the 14 load cases that were run. No issues here. No issues on the shell membrane stress summary, and of course this is where we had the issue, the tube, channel and shell stress summary, no longer in red, no issues, and this issue that we did have is now 0.374 instead of 1.2. So we've resolved our issue. So of course the next thing to do would be to generate our report. That will be exactly the same process as we saw in the previous video.